The idea of a basis of a given vector space is that you can represent any vector in that vector space by linear combinations of the base, basis elements, right? So let's talk about what this symbol means. You have a vector 3, 5. And this can be written as 3 times 1, 0 plus 5 times 0, 1. And therefore, the representation of 3, 5 under this basis A would be 3 and 5. So this symbol means give me the coefficients of the linear combination if you're given a basis. So let's try to do the second one, which is now I want 3, 5 to be something times the first vector 1, -1 in this basis vector beta, or B. And then B times the second one, which is 1, -2. That requires a little bit more calculation than before because now I have to do the scalar multiplication and add them together. So you have A, -A plus B, -2B, and you add them up and you get A plus B, -A minus 2B. So that A plus B must equal to 3. And -A minus 2B must equal to 5. Although you can use REF or other ways to solve, since I've made the numbers simple enough, this should be not so hard to calculate. If you simply add, you get -B equals to 8, so that B is what? -8. You go back and plug it in here, and you get A minus 8 equals to 3, which gives you A equals to 11. And therefore, this is saying 3, 5 is now equal to 11 times 1, -1 minus 8 times 1, 2. Okay. So once you've made this vector as a linear combination of the basis vectors from set the list B, what does that mean? 3, 5, if you represent it as a column vector using this basis B, this should be what and what?
11, -8.
Yeah, 11 and -8. And that's what this symbol means. Is that okay? All right. Then last time I briefly showed you this mysterious matrix where it goes from one matrix representation to another one. But I don't think I gave a good explanation, so let me just do it now. So what is that matrix P? Well, for part B, identity of A to B applied to a vector under A changes this into vector representation under B. So in general, and I'm going to do this tougher case next, but if you have some linear operator T, and you have a basis from the domain and another basis in the target, then you can choose those to represent this matrix as a matrix. And what it does is, if you take any vector v that's represented using A, this calculates T applied to V, and it gives you the representation under B. All right, so it does get complicated, so we will need to go through several examples for this to sink in, okay? But this is our main goal for today. We want to understand what this is saying. Now, note that there are different symbols for this depending on your textbook. Some textbooks would write A to B, because usually arrows go right? Another textbooks would do A and B, like that, or was it the other way? And I hate this one because I always forget which is which. I think it's down to up. I think this means is this to this, like that. Yeah, but was it the other way? I can never figure it out. I don't like this symbol at all. So it's either this or this, but this makes more sense because when A is applied to A, then you get something with B, right? And so the arrow reverse one is the symbol that I like the most. So there are several equivalent ways to write down what I want to write. But of all the different ways of writing it, this is the best one. See, later on, you'll see that if you have a basis, so let's say T is from vector space U to V, T is from U to V, and S is from V to W, so that there's a basis set A for U, and then B for V, and then C for this W. If you have those, then you can do T and then S here. A goes to B, and then B goes to C. And if you do the matrix multiplication, you're going to find that you get the matrix multiplication of the composition of two linear operators, with A going to C. Okay. It's okay if you didn't fully understand what I'm writing here. Eventually we'll figure it out. But my point is, if you have the arrow reversed, it's hard to read it. But here, if you have the arrow going left rather than right, then it's easy to see that A to B and B to C, so these two contract and you just get something from A to C. Right? Okay, so that's the format I like the best. Okay. So that's where we are trying to go to. Oh, and I forgot to mention that, therefore, in the thing that I just erased, what I'm really writing down here is that I have I and V, and then this really should be I times V, but identity times a vector is this vector itself. Identity doesn't do anything, right? Yeah. So that's what it does. And this would be called a transition matrix because you go from one basis vector representation to another one. Okay? Okay? So what would this be? Well, think of it like this. If you have vector space, some vector, say, x comma y, right? Then what is that? V with A would equal to, well, this is same as x times 1, 0, and then plus y times 0, 1, right? So it'll simply be xy. Okay? And that's because this is a very simple set. Right? 1, 0, 0, 1. That's, in R2, that's called the standard basis. Right? So that's not hard. But then, if I want v represented with basis vector b, now here's the trouble I have. I need to write x comma y as something times x comma y, something times 1, negative 1, because we're trying to use b, and then b is this list, right? So I need 1, negative 1 plus b times 1, negative 2. And that gives you x equals to a plus b. And then y would equal to a times negative 1, negative a, b times negative 2, negative 2b. It's exactly like the same situation I just did with the numbers 3 and 5 here, right? And the way you solve it is the same as well. You add them and get x plus y as negative b. So b would be equal to negative x plus y. Plug that back in here, and then you move it to the other side and get x equals to a minus x plus y. Move it to the other side, you get x plus y equal to a. So this calculation shows you that v representation under b is what? What goes here?
2x plus y.
2x plus y, right? What goes here?
Negative x minus
Negative x, negative y. Okay? So, I know that for a given vector x comma y, representation using basis A would be this, whereas representation using basis B would be this. Okay. Now I have to figure out the transition matrix. So this transition matrix is because this operator is from R2 to R2. It's a 2 by 2 matrix. So I need to figure out what these numbers are. Times VA is XY. And that has to be 2x plus y minus x minus y. Okay. So let me give you some time to think about what numbers should be this one. Okay, what's the matrix?
2, 1, negative 1, negative 1.
Yeah, it's 2, 1, negative 1, negative 1, right? If you do across down, you get this, and across down, you get this. Is that okay? Now, I guess another question that you would have is there a simple way to see what's the relationship between this one and this one, right? But it will be clear if we figure this one out. Okay. So, see, oh, I got it backwards. Okay, got it backwards there. See, if the transition from basis A to basis B is called P, then the one that would take the opposite direction would be the P inverse, right? Because if you were to write down I beta to A multiplied to V beta, what would that be? B would be taken to representation in A, right? Is that right? So that would be like they'll be like having this one here and this one there. But that means all you have to do is, if you take the inverse of this and multiply it to the other side, if you move a matrix to the other side, you have to take the inverse, right? So if you take the inverse to the other side, it's exactly what's required up here. So you kind of see that this would be really the inverse matrix of this. So let's try to find the inverse of this matrix. The formula for a 2 by 2 is AD minus BC, so it's 2 times negative 1 minus 1 times negative 1. This times this, right? And then you switch the diagonals. So negative 1 comes here, 2 comes here. And you negate the off diagonals. So it's 1 and negative 1. So negative of negative 1 is positive 1. Negative of 1 is negative 1. You do this, and then this is negative 2 plus 1. So this is 1 over negative 1. That means this just gives you negative 1. So if you multiply negative 1, you get exactly 1 negative 1, 1 negative 2. So that's what you get. Right. Oh, so you realize something. You realize that, so here's the punchline that we just observed. See, if I want the matrix B going to A, it's made up of these column vectors. I just have 2 vectors in this case, where each of the column vectors are, let's call this beta 1 and beta 2, okay? This vector is beta 1 and beta 2. So what those are is the beta 1 is now represented using this basis, and beta 2 is represented using this basis. That's what these are, right? See, 1 negative 1 itself, if you write this as a vector using basis A, what is that? That's 1 and negative 1, isn't that right? And 1 negative 2, if you write it using basis A, again it's 1 comma negative 2. That's exactly the vector you have, right? So that's actually true in general. So since, all right, so let me just erase these parts and just verify for this case. So if that formula is right, this matrix would be, so if this formula is right, this matrix would be, you're trying to rewrite this as, see, A is 1, 0, and you have to represent this using basis vector B, and then the other vector is 0, 1, and you're trying to represent this using basis vector for B as well. Okay, so this should be the formula to get this one. Okay? So I'm just suggesting a different way of getting it rather than doing this. Okay? So let's see if we get the same exact answer that way. Okay, so first of all, 1 comma 0, I want this to be something times 1 negative 1 and something times 1 negative 2. Okay, so that means 1 is equal to A plus B, and 0 is equal to negative A minus 2B. Add them up, you get 1 equals to negative B. So what is B? Negative 1, A, 2. So you get 2 comma negative 1. It's exactly this one, isn't it? Right? So this does give you 2 and negative 1, the first column. Are you following? It's a bit too much. Okay. So now how do you get the other one? 1, negative 1. How do you get 1, negative 1?
You said 0 equals A plus B.
So you need 0, comma 1 represented using linear combination of these two vectors, right? So again, 0 would be A plus B, and 1 would equal to negative A minus 2B. Add them up, you get 1 equals to negative B, so B is negative 1. Plug that in, and you get A as 1. So you get 1, negative 1. That's where this comes from. Let's say you have this question, and let's say we solve this using the transition matrix rather than solving it. Okay. How would you do it? I know that V under the standard one would be just 5 and negative 10, right? So you take the transition matrix that we obtained just now, you multiply it with 5, negative 10, and whatever result you get after this multiplication, these two numbers will be what you had. Okay? So what is that? That's 10 minus 10, so 0, right? Then negative 5 plus 10 is 5. Done. It's a lot easier, right? Okay. So this is the answer.